10 raised to 5 kilometer almost. That is the order, and we have 10 raised to 3 order. That is the size of the and we are almost separated by around 150, isn't it? Million kilometers, isn't it? So that's so radiation from sun is reaching to Earth from that far distance, and so I will so anybody heard about solar constant? So it is the radiation reaching at the top of the atmosphere, so per unit area. So do you know how much may be the value? Rough value? Okay. Before that, let us I will give you an assignment or that thing. So you people calculate the solar constant. So I will give you, this is the sun's luminosity, you can take it, and the earth, the distance from sun and earth, you can take, take this value, you can take it, then you can calculate the solar constant. So basically it is a, the sun is emitted the radiation, that sphere spherically, and that radiation is just projected on the at a particular unit area at a outer atmosphere of the earth. So that's the almost concept of solar constant. And please calculate it and let me know how much you are getting it off. So transmission of energy from the sun is almost radiative nature. So we all know it. So even though there are some mass ejections and all from the sun, but most of the energy is radiative in nature. And these all are that projections what I was telling. So even though in Earth also whatever you are receiving is actually so this much radiation is actually projected over in this much area. Okay, so we have to divide by that factor. So that's why ultimately at the surface we will be reaching on the very near surface will be receiving only 342, that is 1/4 of the solar constant. Okay. I hope that you are getting it. So suppose actually at the top of the atmosphere you have the solar constant, and finally the entire region, if you projecting, this is a circular one, isn't it? And this is yeah, this is projected over this earth actually. Okay, so then this much area it will be, so you have to divide by 4. Okay. So overall, all of you know that energy is conserved, and so in general, most of the time, what happens is that energy is conserved, and no, it is that energy is always conserved, and whatever solar radiation absorbed will be emitted. So we are always in the equilibrium state actually. Okay, so will be, even though some other perturbations comes, then also it will adjust and it will go to another equilibrium. So it is like solar, always the solar radiation absorbed will be always emitted by the our Earth. So if you going to calculate this emission temperature of our Earth, actually it will be around 255 Kelvin. Okay. So before, let us go before, and so we know Stephen Boltzmann's law, isn't it? I hope that everybody knows. So this is the this will be the radiation emitted by our Earth actually. Okay. So then the Earth. Okay. And we can effectively this one you can solve actually. Okay, and because this will be boring if I describe equations. Okay, so you people just go through it. So effective emission temperature will be like this is in terms of solar constant will be something like this. If albedo is alpha, okay. So please calculate it, and timing I will tell you it is like 255. Okay. If you are not, we did not consider any greenhouse effect and only considered this one. Okay. So, but as I told actually, if you consider greenhouse effect and other process, it will be higher. Like what we are expecting is not 255. Theoretical one is this one, but we are not we are experiencing more than that, isn't it? Coming to some general terms, actually, we all are you all know it, but we have to discuss some of the things because atmosphere and related all seasons and everything is linked to Earth's rotation and so how Earth is rotating. So from west to east, isn't it? You can clearly see. Also, annually, we have actually different seasons, and due to the rotation of Earth around the sun. So, let me. There are also equinoxes. So, can you anybody tell what is equinox? Yeah.
Same time of day and night.
Yeah, equal, isn't it? Yeah. So can you somebody else describe something and some more actually?
When sun is near the equator, its location near the equator. So then
yeah, both sides have equal distribution. That's what she was saying. Yeah, it's good. So that is the thing, and that is the condition. And coming to also, let me the next picture here. So here, that March equinox is also there, and September also one is coming. Okay. So do you remember the dates? Yeah, around that. Okay. So find out it just for curiosity. Okay. So that is the thing, and similarly, yeah, the distance from Sun and Earth also varies a lot. Actually. So it is perihelion, and there's such a very far distance actually. Okay, perihelion. So that will be observed around July, isn't it? July 1st and perihelion around 1st January. Okay. So around one. So average distance is even the 150 million kilometers is due to the orbit. It is there are variations in the actual distance between Sun and Earth. Also, I hope that you all know it actually different geographical regions. So you are familiar it, but I will just describe polar regions are there. About actually more terms of ആയിക്കോട്ടെ കുഴപ്പമില്ല ഞാൻ ചെറുതായി തുടങ്ങി പ്ലീസ്. So Antarctic, these people are spent actually there. Here is the Antarctic, and so equator is this region. I think have it actually. So you people explore it. You people discuss, with your colleagues here, and I know most of them are familiar with these things. But still, actually, we should have, as a course, and we should tell it actually. Also, there are changes in long term actually, like axis of rotation, and also these orbital parameters are Milango. They are also known as Milango, and they also have cycles. I mean, it will take a lot of years, but still you can see and so rotation has its own changes, and also rigidity of Earth. So you can see how they vary. Also eccentricity. So these things may not be in a day-to-day basis, but they have impact on a very long run. And so you may be heard about ice age, and so many of them heard it. So these things really impact our atmosphere and climate in a long run. So I think that yeah, we had a very brief, uh, general things about Earth, but now we'll go to the atmosphere. Okay. So this picture shows that this is taken from that International Space Station 2010. So what they see is actually troposphere, and then stratosphere and mesosphere and space station. So this was one of the beautiful things they have actually found, and I'll come into that. What are those layers? And the atmosphere has many layers in terms of due to the characteristics of temperature and other characteristics. So atmosphere is divided into basically previously I told you homosphere and heterosphere. So atmosphere is around 100 kilometers and heterosphere is above 100 meters. And then further divided into troposphere, which is at the 100 kilometers. Meter, sorry, it will be my mistake. It is 100 kilometers. So coming to yeah, different layers. Lowest layer is troposphere. Here you can see that is where we are living, and this. Can you think what may be this one?
Yes.
Yeah, mostly yeah. That may be the probability. I also don't know, but yeah. So what may be the height of Himalayas? So we are living in the troposphere, and most of our human activities are in troposphere, and we are living in the lower part of troposphere. Okay. And coming to stratosphere, actually, so which you people are maybe here, ozone is there, and some characteristics somewhere here actually, or you may be well aware. And many flights, they fly over this stratosphere because it is a stratified region. There is not much convection, and so for flights and all, it is those who are traveling flight, you may be knowing the turbulence is very difficult sometimes. So that thing is not there, and they can easily save fuel and other. Another layer above that is mesosphere. So where actually many meteors deposit, ions and other things, and which is around 50 to 85 kilometers around. And above that, thermosphere is there, and beyond that, it's exosphere. So let me explain troposphere. Many of you people know it. What is troposphere? It is the lowest part of the atmosphere, and you can see the temperature is right side shows its temperature. This one is temperature. Okay, it is increasing up to minus 60 degrees, and this troposphere height, that top of the layer is called as tropopause. So top of layer is known as tropopause, and it is located in tropical regions, and it is located about 15 kilometers, 16 kilometers like that. But in higher latitudes, so it will be less like 10 kilometers. Like so, there are variations with the regions, latitude center, and above that is the stratosphere, and above top of that is called as stratopause. Okay, so that is located up to around 50 kilometer altitude. Okay, so you can see temperature is increasing due to the ozone, because ozone production is there, and that absorbs radiation, and temperature is nothing but it is the average kinetic energy of molecules, isn't it? So that's why they are excited, and they have more kinetic energy temperature. Then further it is decreasing. So here actually there is no process of solar major absorbment of solar radiation, but then what happens actually? Cooling is mainly due to radiation emitted by the gases there, especially CO2 and again thermosphere. After that, ionized particles are there, because solar radiation come and X-rays and come and hit directly. So there is no way to these molecules cannot escape. They will be ionized, and temperature will be they are directly hitting. So they have high temperatures, and the temperature is gradually increasing in the thermosphere. Also in troposphere, what happens? Temperature increases at a global rate at around 6.5 degree Kelvin. Okay, that is also called as lapse rate. So tropospheric lapse rate, average lapse rate is around 6.5 degrees. So, but actually, if in a theoretical way, you may be heard about adiabatic process. So, in adiabatic process, what happens? Yeah, it's if a moisture is not there, and so lapse rate will be much higher. So it will around 9.8 degree change will be there per kilometer. Okay. Also, we should we should remember we all are living in boundary layer. So which is the lowest layer around 1 kilometer or some. It also there are changes, spatially changes are there. So we are now living in boundary layer of the troposphere, actually which is defined as the tropospheric layer, which is directly influenced by the presence of Earth's surface. So like friction and other parameters, okay, and respond to the surface forcing in an hour or less. Okay. So it is very clearly defined in terms of friction and like response, like solar heating. Okay. So that is the one thing. This boundary layer concept is very similar to that of fluid dynamics we all studied in schools and other plus two and other things. Okay. So coming to stratosphere in detail, so I already mentioned that jets and all fly over that region. That does not mean that while we are taking off, we are directly going to stratosphere. Okay, so only that long whatever long flights only will go mainly travel at that altitude. Okay, and the second is that the main thing of this layer is that maximum ozone, so more what we call as ozone region in the atmosphere, so which is located at the altitude of say around 25, isn't it? So that is the one of the important point, and that is has a vital role in its it is saving a lot of Earth surface from severe radiations, especially UV radiations. So I'll come to the interactions, but let me tell you this UV light interaction with ozone is causing the temperature increase in the layer. And before we have seen that there is a in lower level like troposphere temperature was decreasing, but here it is just it was decreasing in lower level and it is now increasing. It is just inverse. Okay. So that is the one of the particular characteristics of this layer, and it is more stratified because it is stable now compared to the previous troposphere. This becomes more stratified and more uniformly distributed. Okay. So let me just tell a few words about ozone because we cannot miss ozone in atmosphere, so especially stratosphere. So this ozone layer is we can define as the region where maximum concentration is seen, and basic production of ozone in the atmosphere in that level is happening due to Chapman reaction. So this always remember Chapman reaction. It is nothing but very simple. So due to ultraviolet radiations, ozone, some of the oxygen molecules will break separately and becomes atomic oxygen. Okay, and then what happens? They will combine and form ozone. So two-step process. Just three molecules of O2 is in the presence of sunlight is converted to two molecules of ozone. That is happening there. Also, UV itself, there are different, spectrum has different components like UVC, UVB, and UVA. And we can see that UVC is one of the, major that energy carrying UV. So, which is attenuated there itself within the ozone, within the stratosphere itself. And also then coming to by the just about tropopause that UVB also attenuated, and higher wavelength actually region UVA, so which will be coming even up to certain level of troposphere. So so let me ask one question. So which one may have more energy? UV, these wavelengths are given here. UVC is UVB and UVA. C. So C may have more energy because wavelength is less. Wavelength is less means frequency is more, isn't it? So if something has to do more work actually, so which may have more energy, isn't it? So one number of oscillations. Okay, so it will alternate there itself, and longer wavelength will move. That is the general thing. And I'm some of the things I am skipping it because coming to mesosphere, and this is one of the part of the atmosphere. Still, a lot of gap areas are there because the main reason is that we don't have frequent measurements there. Balloons will not go there because it will mostly burst at stratosphere. Main thing people use is actually this sounding rockets. From ESSC also people will sometimes launch and study this. And the satellites also not there in this this altitude. So that is one of the limitations. So this mesosphere has a lot of physics to understand, and we really want to understand mesosphere. But that is in future people may be doing it. I hope. So, but this layer is mainly observed over, like as I mentioned, so 50 to 85 kilometers. And one of the most important thing in the atmosphere, this is the coldest part. So, which has around minus 90 degrees centigrade. So, this is mainly due to the cooling effect due to radiation, isn't it? Radiative cooling. And also sometimes, I come to middle atmosphere. There is a term called middle atmosphere. So middle atmosphere is, basically come from combining stratosphere and mesosphere. So combining the process related to that. Also, one of the rare clouds, these polar mesospheric clouds, and are also observed in mesosphere near the pole center. So that is very rare, but still, actually, they are the highest, very high altitude clouds ever observed in this atmosphere. The atmosphere is just above, yeah, mesosphere, and that is the almost we can say the upper portion of the atmosphere. And basic reason is that X-rays and UV radiation from are directly hitting this atmosphere part, and they are excited and they will ionize and many times, and very so that is the reason for formation of this atmosphere. And so obviously once somebody get kinetic energy, they have more temperatures, and obviously temperature will be increased. And temperature is going, yeah, up to 500 degrees and to even 2000 degrees. So beyond that, exosphere is there, where actually it is not like ionosphere. Actually, it is like particles may be unevenly distributed, or even atmospheric gases may be leaking through this region sometimes to the space. Also, intermediately, I mean, even though this cannot be called as a layer, but this term is very important, ionosphere. So this ionosphere is basically part where actually we have ionized air molecules or whatever atoms are there. Okay, so this has vital role in communication to satellites and radio communication and many things. You all maybe studied in colleges and about ionosphere, how they are important in radio communication and all. That itself has different subcomponents, like D layer is the lowest layer, and above that E layer is there. So D layer is located around some 70 to 80 kilometers, or maybe sorry 60 to 70 kilometers that range, and yeah, E region is 90 to 100 kilometers, and approximately that is the range. Okay, and I will tell you one more thing. There is no sharp boundaries for atmosphere. Atmosphere is a fluid, so we cannot have fixed the this is my troposphere and this is my stratosphere. It will always vary here and there. Okay. And above that is F layer. Okay, so F layer is around 50 kilometer. I think we start from that range. So most of the times, actually, F region is most prominent, and they will be always there because due to solar continuous availability of solar radiation, and it can be always there. But other regions, B and E, they have actually diurnal variations due to if sun sets actually. So definitely there is a recombination, and there will be a little bit, ionization will be reduced, and they may disappear also, especially the region. And so he becomes relatively weaker during night time, and these are some of the, previously I told you, people are maybe knowing how this ionosphere is helping for radio communication and all. So which reflects, this radio waves, which is vital for long transmission of, you may be getting even previous time energy if you do naturally you get from radio from Sri Lanka and other places also. I don't know now somebody anybody hear radio now? Okay. Anyway, I hear it. So okay. This also some concept of this one depending on if for example if D region is active suppose it will be reflected here itself, okay. But if it is not there in night, actually if it is not there, so it will go more distance, so it may be reflected from F region, okay. So more coverage will be there. That's why nighttime and that sometimes you may get from far region, you can listen that radio and far stations. Yeah, this was a general overview of vertical things. So you people may prepare your own, I hope that do you have any doubt or do you have any other discussion items in vertical structure? Okay. So now I will just go to the composition of the atmosphere. So main components are listed here actually. So in terms of, see, also note that actually most of these variables people will say in terms of unit also as a research fellows or always not, unit of the variable. Okay. So here this is presented in percentage by volume. Okay. And nitrogen is around 78 percentage, and oxygen is like 20.95, and argon is 0.93. Neon is, these four are main components in the atmosphere, and minor components are the helium, hydrogen, xenon, and also these are permanent gases. They are called as permanent gases. Okay. At the same time, there are variable gases due to various processes of the atmosphere, like water vapor, natural and other activity, and it will vary from 0 to 4%. That is one of the major water vapor is one of the major greenhouse gas, and carbon dioxide and methane, nitrous oxide, ozone. So ozone is also one of the things. Previously, I have told about ozone, but troposphere also has ozone. It is, that tropospheric ozone is not that good like ozone, at the stratosphere. So that's also you should remember. Okay. And yeah, it also has suspended particles like aerosols and other things. And so there are many components, but major components are like nitrogen, oxygen, and so if you calculate how much will be the total average weight of the each air, so it is like molecular weight comes around 28.96 gram per mole. So if you remove, if you tell in terms of gram, it will be 28.96. Okay. So which is much higher than no, water, isn't it? Water vapor. So how much water? Do you remember how much is molecular weight of water? 18. Yeah. 16 plus 1 plus 1, isn't it? Yes. So yeah. 16 O2, then 2 hydrogen. So 18. Yeah. So 18 is the thing, and so this has 28. So suppose this is the dry air meet with has some water vapor is if you are introducing, what will happen? One's weight is like 28. One's weight is 18 only. So obviously what happens? Yeah, it will go up due to buoyancy, isn't it? Water vapor will, yeah. So that is the one of the important thing we have to understand, because this has a lot of implications in atmospheric convection and other processes. Okay, convection, especially the buoyancy. Once you add, that is simple enough to due to its molecular weight itself, they have tendency to go up. So I'm just introducing some of the terms. Okay, so just going one to another. Okay, so you may feel a little bit is jumping from another topic. But pressure is one of the variable we should understand in atmosphere. So can anybody tell what is atmospheric pressure or pressure or something? that is the simple concept. So the whatever weight is there throughout the entire atmosphere. So what is acting on, isn't it? So that is that. So this is the vertical profile of with altitude there is a change in pressure, because if you are actually trucking, you may be faced actually that the change in pressure, isn't it? Or even if you are going in flight, you may be seeing that you get some changes in pressure, and here you'll be able to identify the pressure change. Okay. And surface level pressure is very important parameter. We all should understand. Pardon? Hello. Hello. ഹാളിലേക്ക് വന്നാൽ മതി. അത് സെക്യൂരിറ്റിയോട് പറഞ്ഞു. So the speaker is coming. So while a few slides I will close my. So always learn actually what is your understanding is good, but it's good to have a different views. Okay, on this thing. Okay. And this is one of the relation connecting pressure at a particular height. For example, 10 kilometer. What is the pressure? So this shows that P into P0 into units. This term actually will come. Okay. So I'll come to that another form of that equation. Okay. Another thing is that we all know that if there is no other convective movement and the air is not rising and okay, if it is in a equilibrium state, okay, what happens is that gravity pulls atmosphere down, atmospheric molecules and yeah, please. Yeah, please. Sorry that we thought that we will call you. Okay, you take your own time. I will a few slides. I will finish it. So as I mentioned, gravity pulls air atmosphere to down, isn't it? So gravitational force will be there down. Okay. At the same time, pressure is exponentially decreasing, isn't it? So that's what we found here. So it is decreasing exponentially, isn't it? So this there will be that force is called pressure gradient force. Due to gradient, okay, gradients in pressure, there is will be force will be there. So that will be acting just opposite to that. Okay. So it will be in equilibrium. They are due to this equilibrium condition. That is that particular situation is called as hydrostatic equilibrium condition. Okay. So this is one of the basic concept in atmosphere. If there is no convection, it's the ideal case. Ideal case, it is for describing ourselves. It may happen or it may not happen. Okay. So, but this is for the fundamental concept. If this is the condition. So, gravity and pressure gradient is there. Okay. This is valid only for a large scale. Okay, very large scale in nature, not at a very fine like 1 kilometer, and it may not be valid at all. And this is not right side figures are not anything related to this one, but this is for showing how this force is acting. So, like high pressure to low pressure, net force will be towards that thing. Like as I first telling, this force is from towards up. Okay. Also, if we are this is also if suppose this is a region. Okay. So high pressure region is there this side and low is there. Obviously, wind will flow from that high to low pressure area. Oh. Anyway, this one is in terms of this cartoon shows that high pressure has more number of that air is there and air relatively is just cartoon representation. So another, typical term is that gravitational potential. So this is considered as the gravitational potential energy per unit mass. And anyway, I will just time being, I will summarize. Some, okay. So time being, what I'll stop with this one. Okay, and she will start. Okay. So comes to the elements of weather. Temperature is one of the parameters. Okay. So because we should have for everything we should have some measurement. Isn't it? Some parameters is required to quantify or qualify or assess or something like that. So yeah, one is temperature is the such parameter for atmosphere, and which is nothing but hotness or coldness of air. Okay. So if you more go to the physics, it is more like nothing but the average kinetic energy of the molecules. Okay. So that may be more valuable for science people. Okay. So always remember in that whenever you get energy, you will run. Okay. So that is the key. So and second is humidity is the one of the parameter because due to the buoyancy as a vital role in clouds and other things. So that has more implications in atmosphere. And precipitation, we always look for precipitation as a human being, and water is one of the major resource for us. So that is the main source actually for precipitation is source for that. And wind is the movement of air. So wind has two characteristics: speed and direction. So atmosphere, one thing you should remember is that there are many conventions actually. So how we deploy. In oceanography, it is a different perspective, and this one and some other topics will be different. So this is here people say the reference is something like this. From where it is coming. So from where it comes, for southwest monsoon, we call, okay, that's a wind, okay. So it is coming from southwest direction, okay. So that is its meaning. So, but it will be different in different areas. So it's not that from where it comes, that also matters. Also, this has a meaning. For example, if something comes from southwest, it have its own characteristics. But if it is coming from, for example, for us it is like Arabian Sea. So that wind has a particular characteristic. If it is coming southeast, like Tamil Nadu and other regions, it is coming to Kerala. So which has a different, yeah, characteristics. Okay. Also another is dew point, which is also measure of water vapor and that uh, that water vapor in the atmosphere. And cloud cover also we are also one of the important parameters. I will stop with this one. As I told you, wind is one of the important parameters. So actually here people resolve and use this one. The wind will be resolved into two components. X component is U, and the Y component is what is normally called as U component actually. Yeah, zonal wind. Okay. What is Y component actually? Meridian. So always remember actually whatever uh, this wind is actually colors U wind, and this colors V wind. Okay. So its direction is also same way. Coming from west to east is this direction is positive. Okay. If it is just east to west, it will be negative. Okay. Similarly, this one V will be also same way. This will be positive. Northern side will be positive. Okay. Coming from north to south, it will be negative. Okay. And so if you are telling in terms of wind speed and direction, so then how wind direction will be measured is also unique in meteorology. See, it is measured from north to north, east, south, west, this direction. Okay, like almost clockwise, isn't it? So this is from north direction. Okay. So see, from south means it will be almost like 180 degree, isn't it? So also you can resolve the components according to your wish. Okay. That so this is very basic mathematics, school level or first school level. Okay. So I will just skip it and I will hand over to also, who can describe latitude and longitude typing? Who can volunteer? Use this one. Who will do it? Somebody should do it. Okay. No, just you all know it. It's no, but still, yeah, I will just remembering ourselves. Okay. See,
How many hours in a day? 24. How many longitudes? 360 divided.
yeah, that's right. That's a very simple way. Okay. So, yeah. So locations also you should know it actually. This central region, equator. Okay. These are poles, isn't it? This is North Pole and this is South Pole. These people went here, isn't it? So,
I went to North Pole.
North also. Okay, very good. So, latitudes are something, moving like this, isn't it? And the longitudes are something.
No. Latitudes are moving.
No, if you move from like pole to pole, it means you are varying from latitude wise. That is the answer.
Yeah,
That is
this
not
variation I am saying. Okay.
sometimes people have confusion like that. If you are moving like that, then it's a varying. Your varying latitude will vary. Whatever concept you have, you can keep in your mind. But latitude means like pole to pole variation.
Yeah,
If you are
that's what I
moving
was
from one
saying.
pole to two poles, it's varying from latitude.
And it's all start from the parallel center. So you may be knowing the concept. Also, more important is that the projections and what you are using. See the area. Our Earth has a different type. It's, like many of us, a bulging at center. Okay, and it's moving. Towards polar region, it is smaller in size. Okay, that box size you see is very smaller. Okay. So that's why many flights and they are going from Delhi to somewhere US or even far regions. They will fly over not straight like this. They will fly like around polar region and they will come. So if you even in Google map, if you measure the distance, direct distance will be much more. Yeah, this is because of the shape of projection. So first of all, let me introduce Dr. Anila. So Dr. Anila has completed PhD from SAT and well-known and his book also Stratosphere book is well known. So she is now presently working as a scientist in CWRDM, KSCSTE, and she has many publications. And so I will welcome her for the talk.
So I was also trying to like give an introduction to meteorology. So I think he has given all the things, basic things. Sorry, I missed my bus. I couldn't get in time. So traffic block was there. Just you are all from geosciences background.
Yeah, different people are there. Actually,
Okay.
different streams are there.
Like these are only really basics, as we told, only the basic concepts of, because basically atmosphere is a fluid that occurs and also thermodynamics and this atmospheric dynamics, geophysical fluid dynamic principles. So just I'll be showing some basic laws or basic variables that govern the atmosphere. First, then if you're getting time, I will go to another presentation with some more, it's more colorful about some climate change and things like that. So basically, you know, the atmosphere is like a peel to our Earth. You know, it is like an orange peel. It's nearly the size of an orange peel, above an orange compared to the size. If you are comparing the size of the Earth to that of its atmosphere, it is really a skin to the atmosphere. It's a gaseous envelope, and also it is gravitationally bound to the Earth. So basically, so the first force we will be thinking of is gravity. One of the major force in the atmosphere is gravity, and also the state variables, that is the conditions that represent or the conditions that determine the state of the atmosphere. The basic variables are pressure, temperature, density, and moisture. So all these are interconnected or related, because the temperature variations will be determining the pressure conditions, the motion of the air molecules. You know, basically the energy of the molecules, energy of a molecule depends on its state of how much energy it is having, depends on how much temperature is there. So basically that will determine the movement of the molecules. So the motion of molecules from one place to another place will be determining the weight of the molecules or above a certain portion, above a certain area of the atmosphere, that will be determined by the temperature. The temperature, the energy, if it is getting energy, it is moving to some other place, that will determine the pressure, the weight exerted by the molecules above a surface. So that is connected with temperature. And similarly, the density, how much molecules it is holding, that is also dependent. And of course, the moisture, that is, you all know that we say about this climate change, the moisture holding capacity of the atmosphere, because if it is having more temperature, it will be having the more, what it will be having, how much moisture will be there if temperature is. So if the temperature is more, the moisture will be more or less. More. Okay. So all these are interdependent. So basically, meteorology is the study of the mechanics, physics, and chemistry of the atmosphere. And you know that you may have seen this figure many times. The major components of the atmosphere are basically nitrogen and oxygen. So these are like somewhat, they don't have that much role in determining the temperature. It's only they stays in the background. They are actually somewhat what to say, they are not having that much effect on the dynamics or thermodynamics or things like that. Basically, the trace that is above that oxygen, nitrogen, and this inert, some gases which like argon, that is less than 1% or 0.93%. But they are all like inert or somewhat what to say, having less effect in the climate or state of the atmosphere. But what determines the state or temperature of the atmosphere, what is more detrimental, is gases like carbon dioxide and water vapor. They are having a concentration of less than 1% in the atmosphere. But they are very much responsive to the radiation, the incoming, the outgoing long wave radiation. You all know that the sun is radiating energy towards us, and the Earth's surface is absorbing that radiation and radiating it as long wave radiation back to the atmosphere. So this carbon, the gases like carbon dioxide and water vapor are having more interaction. They are more interactive with this radiation, and they determine the temperature profile or the temperature of the atmosphere. So water vapor is like carbon dioxide. Its concentration is like it mixes rapidly, and it is like its concentration is always or nearly uniform. That is, if it is near the surface, it will be more, and in the profile it decreases with the height. But this water vapor is highly variable. It's one of the highly variable greenhouse gas. All these gases that are reacting with this outgoing long wave radiation are called greenhouse gases. So, and the another important component of the atmosphere are aerosols. So, what is the role of aerosol? What is the impact they are having? Anyone who can tell? Aerosols are suspended particles.
Changing the radiative balance of the atmosphere.
Atmosphere, yes. So we are changing the radiative balance of the atmosphere. That is one point. So aerosols like black carbon aerosols, they are actually having a positive radiative forcing. That is, they increase the temperature. They actually absorb the incoming outgoing long wave radiation. That is the heat radiation or infrared radiation from the surface of the Earth, and they retain this radiation inside the atmosphere. It's black, almost all the aerosols, but some other aerosols like sulfate aerosols, they are having a negative radiative force. Okay, they will be lessening the radiation. They will absorb more incoming radiation also. Some aerosols. So another aspect of aerosols is they act as they are having. There also it is written they are acts as cloud condensation. Okay, they are this some aerosols are like they are having an affinity towards water. They will be absorbing more water inside the clouds, and they are retaining that water around it, and allows the water to build up as it moves upwards due to this convective activity. So, and when that water reaches enough size, it will be falling as rain. So, these type of aerosols act as cloud condensation. So, this is basically the composition of the atmosphere, and maybe in a second that this vertical structure and thermodynamics. In that, first comes is the vertical profile of temperature or the structure. The structure of the atmosphere is defined by which parameter? Which parameter? First, when we say about the structure of the atmosphere, it is defined as the change in temperature with height. So, the different layers of atmosphere are classified according to how much the temperature varies within each of the layers. So, first layer is the troposphere. It is the lowest layer. Actually, the height of the troposphere is up to nearly, it will be more over the equator, and it decreases towards the poles. Do you know why? Yeah. No.
And temperature is solar radiation.
Yes. Temperature. Yes. So the temperature will be decreasing because the equator receives more heat. So there will be more like that temperature is there. That will be giving that interaction over that temperature will be giving more heat to the atmosphere, and hence the temperature will be increasing to a more height compared to the poles in the equator region, and it will be decreasing progressively and it reaches up to 8 km in the polar regions. So that is troposphere, and the next layer is the stratosphere. So the stratosphere, it is written there as it is increasing in temperature. So you may have heard about ozone layer. Ozone layer is present in the stratosphere, and because of the presence of ozone layer, the temperature, like ozone absorbs this radiation, and as the concentration increases, the temperature is also increasing towards the height, and some oxygen is also responsible for this temperature gradient, because the ozone layer lies somewhat in middle of the stratosphere. Above that, because of the presence of oxygen, that is also contributing to some radiation, ultraviolet radiation absorption, that gives the increasing temperature profile for the stratosphere. And next is the mesosphere. Here, temperature usually that it decreases with the height, and it reaches up to like 80 kilometers. It will be above that, it is the thermosphere. Here again, the temperature will be increasing with height. The profile we can see there, and also the pressure. We can see that the pressure also it is having that what like somewhat a log is like what to say, increasing with that height, because the air molecules, the weight of the air molecules due to this temperature profile, and also the weight of the air column above the atmosphere decreases. With that, the weight of the air column decreases with height. With that, the pressure also will be decreased. And this also, I think, he has taken. This is about the convention of the next thing. This is we said about temperature. Next is this is about wind. So in meteorology, we will be the convention is different from that of conventional mathematics. We will be taking the directions in a different way. So here the local Cartesian coordinates, we can, you know that Earth is a sphere. So usually if we are considering very much large distances or very hemispherical movements, we will be considering the spherical coordinates. But for local, very local, like a town or a province or a small city or something like that, we can mention that in Cartesian coordinates. So here the velocity component, we usually take the u component, the horizontal velocity component or u component from towards east. That is the positive direction is east, and uh, the vertical, not the z component, the y direction component is from south to north. It is taken as from south to north. It is, we will give it the term. The horizontal component, the zonal component is u. The other one is v, and the vertical component z is from surface to upwards. That is w. So here we can, when converting these two polar coordinates, we can convert that using that equation given there, that is m is equal to u square plus v square, that's the square root of u square plus v square, and also the magnitude is that, and the direction we can compute using that equation. And that is that a0, that constant is the value. If the value is u is greater than 0, then we can give that value, that alpha 0 is equal to 180 degrees centigrade, and c is the angular rotation, the constant, that is equal to 360 degrees, is equal to 2 pi radians. And also here I have given that conventional mathematical and meteorological angles. In conventional mathematics, we can see that the 0 degree is towards this direction, and we are moving in a counterclockwise direction for conventional mathematical purposes. But for in meteorology, we will be taking 0 degree in this direction, and the direction will be, we will be taking in a clockwise direction. That is the meteorological convention. And also, one other thing is like the direction we usually say, if we say easterly, then that is from which direction wind is coming from? East. From east. Okay. So that is also there. That is the direction from which the wind is coming is like that is taken as the direction, that easterly, or the wind is coming from west, it is westerly. Not the direction towards it is going. the direction from which it is coming is taken as direction of the wind. And we know that when a group of molecules they move in same direction, that is called wind. When they move in random directions, that is we said earlier, due to pressure differences, the air molecules or air masses will be moving from high pressure towards low pressure. That is there. But the if the internal motion inside an air mass in random directions may be due to the energy it is having, that is the temperature of the atmosphere. Okay, so that random movement determines the temperature of the air particles. So one of the major thermodynamic variable is temperature, and when the temperature increases, the speed will be average molecular speed will be increasing. So that is a constant. That is temperature is proportional to the velocity square, and it is determined or given by that equation. That is A is a constant, and that mW is the molecular weight of the gas. Okay, if it is air, it will be substituted by the molecular weight of air. Okay, and V square, that is the velocity. So another variable is pressure. So you all know the basic definition of pressure. Pressure is force per unit area. So the pressure exerted by the atmosphere is basically the atmospheric pressure. So it is caused by that movement of like the weight exerted by the air molecules. We see that here I have given that that air molecule is having that pressure, that force, that static pressure, that component in all directions. The pressure is having components in all directions, but only the normal component will be having an effect. All other components will be like cancelling each other. That is, we can see there. Only the normal component, it is not cancelled. It is actually having a variation. All other components will be cancelled by each other. So only the normal component of pressure will be determining the upward gradient of that pressure. And also here we can see both this that equation is also this will be representing the pressure at a height. Okay, having this temperature, this is the pressure at the surface, and it varies exponentially with height. So this is the variation of pressure. This is the same variation in pressure in a semi-log axis. Here we can see that it is varying in a straight line. That semi-log distribution is there. It is varying in a straight line in a semi-log axis. Otherwise, we can see that exponential variation. And also, this is the equation that determines the variation of pressure with height. And this the unit of pressure is Newton per meter square or Pascal. So usually, conventionally, the in meteorology, kilopascal is used. That is 100,000, and also another unit is hectopascal. That is kilopascal, like what to say, one decimal point next to kilopascal. That is into 10 is hectopascal. If you want to convert to kilopascal, just move a decimal point to the. So this we have seen that pressure variation is with the height. So but if temperature is uniform with height, we can represent with that equation, and the values of constant A is this 0.0342, and this pressure at the surface is here, it is written kilopascal, that is 101.325 kilopascal or 1,013.25 hectopascal. So okay, this can be rewritten as this one, that is divided by HP. That the above equation can be rewritten as rewritten in terms of this a parameter called scale height. That is how much the what to say, the it is a measure of how much the temperature, the pressure is varying with height. That is having actually a value called 7.29 kilometer. That is the pressure varies with a scale of 7.29 kilometer with the height. So you can rewrite that with the above equation in terms of scale height, and the value also can be given as HP is equal to 7.29. Actually, HP is the e-folding distance of the pressure curve. We have seen that pressure curve here. That variation can be typically represented by this scale height. Hence, it is rewritten in terms of this, and the value is also we can substitute this in any calculations and all. So another variable. So we said about pressure and temperature, and another variable is density. So density, we know that mass per volume. Okay, mass per volume is density. So unit is also kilogram per meter cube, and the equations previously we said about pressure. Similarly, the equation is written the variation of density with height in terms of temperature as well as scale height. Both equations are given there, and also the variation similarly represents to this curve is representing the previous it is resembling the previous one also. Right. This is the variation in density, and the constant value is also it is given. That is, the standard values are 288 Kelvin, and the sea level density is 1.2250 kilogram per meter cube. So this is the standard atmosphere. That is the pressure, temperature. We have actually calculated, or we are assuming in many calculations we will be taking the case of standard atmosphere. So we will be representing, or we will be taking these constants at different heights. At 0 kilometer, we will be the standard. There are different standard atmospheres are there. Different what to say, represented different conventions are there. This is one convention. So this is US standard atmosphere. So here we can see that that 0 level, on height at 0 level, the temperature is 15 degree. Pressure we said earlier, it is 1013.25 hectopascal, or the kilopascal unit is given there, and the density also is there. So if we give a problem of calculating the pressure, temperature, or like that, we can use these approximations. Okay, in any of the calculations. So another parameter or another term is the basic to the meteorological studies are geopotential height. So we know that Earth is having a gravity. So Earth is having a gravitational pull to any object above it. So if we take one object against gravity, it will be gaining a which kind of energy it gains when we lift? Potential energy. So it works against gravity, and it is gaining a that potential energy, right? So usually we will be giving this term. We need to calculate, or we need to give a constant value to this gravity, constant of gravity G. But it is used not that is the gravitational pull same in all the heights? Earth is pulling with the same intensity in all the heights? No, that gravity, the G value is decreasing with height. So we cannot give that constant value. Okay. So we will be giving an we will be taking an approximate height called geopotential height that takes the gravity as a constant. Okay. And that gravity will be treated as a constant. So that H is the what to say, it is if it is lifted with a constant, that is if an object is lifted against gravity it is called, that height is called Z. Okay, that gravity will be, that height G will be varying with height. But if we the geopotential height is the same height, if it is pushed, if it is gaining the same potential energy with same gravitational pull towards this height. That is, if we are taking it against gravity and it is reaching a certain height, is okay. So here we consider the variation in gravity. So that same energy it will be if it is gaining with the some other height with constant gravity. Okay, that is called potential geopotential height, because it is having that the same energy it will be gaining. We are giving an approximation. It is gaining the same energy with constant gravity. Okay, so usually that difference will be approximately 0 to 16 meter. Okay, if we are taking it is that geopotential height difference between geometric height and geopotential height will be will be between 0 to 16 meter, as height increases from 0 to 10 kilometer from above sea level. Because we are giving, we need to take gravity, we need to consider the gravity constant. So we will be giving an approximation to the height to make this gravity, consider this gravity constant. Okay. So it will be having the same potential energy as if it is lifted to only a height of h under constant gravitational acceleration. So an object lifted with a certain potential energy is that if we are lifting another with same gravitational force, it will be, both will be having the same potential energy, but one is having that geopotential height and another is having that geometric height. So another this thing is like we combine both the gravitational force and like the gravitational constant and geopotential to give rise to a new variable called geopotential. So it is like the gravity, the value of gravity into h. It is the work done against gravity to lift 1 kilogram mass of air from sea level up to a height of h. And it is its unit is meter square per second square. So it is another term we usually use in meteorology. So you all know about boundary layer, right? So all these parameters like the standard atmosphere or the variation in pressure or temperature, all these are having a profile. We said all of that. But the drag from the friction and the other fluxes, the temperature near the surface, the radiation, the heat generated by like our activities, all this remains near the surface. So that layer up to like from bottom layer of the atmosphere up to approximately 3 kilometers is called atmospheric boundary layer. All the turbulence, all the energy or the heat and all the processes, all the transport, all this happens due to human activities or the surface soil atmosphere interactions. All these things happen in this boundary layer. So that profile that of basic, all these basic variables will be changing in the boundary layer. So it feels the effect of the surface, slows the wind due to surface drag. So surface drag will be there because the airflow will be obstructed by the surface, the friction will be there, terrain will be there. All these things will be changing all the atmospheric parameters, all random mixing will be there. All this happens in the air mixing will be there. All this happens in the boundary layer. And like pollutant transport, all these things happen. So it is one of the very like what to say, it's constantly varying. All these parameters will be constantly varying, and also one of the dynamic, most of the highly dynamic layers of the atmosphere, which is a lower layer called boundary layer. So next we know that this equation of state or ideal gas law. So study, or we will be understanding the atmospheric parameters from basically the ideal situation, because atmosphere is a gas, so the governing equation, basic governing equation we consider is the thermodynamic equation is the ideal gas law only. So here first we will consider that it is dry air, that is no water vapor is present. So then the ideal gas law is like we all know that gas constant, that is pressure, is directly proportional to temperature, and we will give that density there and the gas constant there. So that RD, first line, that RD is, this is the gas constant value is given here. This is a gas constant for dry air. So this unit for temperature is usually standard is Kelvin, and total air pressure heat here is what means by this air pressure is the sum of all the partial pressures of all the components or all the ingredients we said earlier, or the composition. So all the sum of the partial pressures of all the components will be is represented here as P. So similar, we know that atmosphere is not dry, right? It is having water vapor. So a similar equation, if we represent for water vapor or for moist air, we will be changing that suffixes, that is PV, RB, and T. That is the density of water vapor and gas constant for water vapor and temperature. So here also this gas constant, when water vapor is present in an air mass, the gas constant is not constant, like that the value of R will be varying. So to approximate for that, or to simplify the things, so sorry, the temperature will be changing, that is gas constant, that temperature also will be changing. So because of the presence of water vapor, and the value of gas constant is also does not remain constant. So to approximate for that, we will add, or we will simply give an approximation to temperature, that is the virtual temperature. Or here also the virtual temperature, the equation is this, and we will be giving the mass, this R is the mass of water vapor by mass of dry air, this one, and also this A is the constant we have given the values earlier, 0.04. Earlier slide the value is given that to that constant A. So, sorry, that is for another value. Here the A is 0.61 gram of dry air per gram of water vapor for dry air. That constant is for some other. But here also I have given the same variables, so that confusion to you. So all the values can be given. This is just an approximation to account for the presence of water vapor in the air mass. So we will be changing that. Okay, considering the this virtual temperature, we will be changing or rewriting the gas law as the pressure of the like the representing the gas law as our ideal gas law, converting that to this rho RD and TV. Here TV is the potential, the virtual temperature, and R is the still the gas constant of dry air. So with this, with the involvement of this, after involving the pressure, this virtual temperature, we can consider the gas constant as same, because we are accounting that in the calculation or computation of that virtual temperature. Okay, this we have, I think we have seen that hydrostatic equilibrium, that is the pressure, that vertical pressure gradient is there. So the basically the hydrostatic equilibrium prevails everywhere, except from this like extreme weather or conditions are there. Otherwise, atmosphere obeys the hydrostatic law. So here also the force we can represent the forces that is F is equal to mg, g is the gravitational constant, and we earlier we have seen this, that is the what to say, if we are having it, if we consider a thin slice of air in a height, and like that thickness of the air as that air slice as delta z, then we can see that change in pressure or the gradient of pressure in that height. Here it basically defines the pressure gradient. So here we can calculate that hydrostatic equation, or the change in pressure over the thin slice of air in a height is pressure, the density into gravitational constant into that change in height. So this is basically the hydrostatic equation, because it is like a balance between that pressure gradient and gravitational force. It represents a balance between the pressure gradient and gravitational force. That is, pressure is pushing upwards and gravitational force is pulling down. Both these forces are balanced, and we can define the pressure or the what to say, density of a layer. We can we can define the pressure change or the change in pressure of a certain height using these equations, the hydrostatic equation. When we combine the both the ideal gas law and the hydrostatic equation, both are both. If we combine both, then we will get the hypsometric equation. This will be giving you that how pressure varies height with that you know, the temperature. Usually we like the temperature gradient is not constant; it is varying arbitrarily. So that the real life condition, if we want to compute, we can use the hypsometric equation. That will be that's a combination of both the gravitational equation, sorry, the ideal gas law and the hydrostatic equation. So here we will be giving that constant, that will be that value is 0.61 we have seen earlier, and that virtual temperature is there, and the like the ratio, logarithmic ratio of pressure 1, that is lower, and the what's the pressure of a lower layer, two pressure levels, lower layer pressure and higher level pressure. So this equation gives like that is the thickness, that is the difference between the pressure. You know, the pressure is a surrogate for the height also, because always the pressure variation is changing with the height. It is corresponds to the like what to say, we have seen both the graphs. It is like it corresponds to the changes in height, so it is always a surrogate of change in height. So we can say the two layers, that is the thickness, the pressure difference, pressure thickness, we can compute using the hypsometric equation. So you know about lapse rate, that is the change in temperature with height. It is called lapse rate. So certain like the usually we say this environmental lapse rate. There are three terms it is written there. Environmental lapse rate is there, dry adiabatic lapse rate is there, and moist adiabatic lapse rate is there. So when we consider, usually when we study all this convectional movement or convection activity, movement of clouds or movement of air, formation of clouds or movement of air passes upwards, we consider the like if the parcel moves upwards in an unsaturated state, that it contains water molecules and it only it is not saturated. Okay, then we consider the dry adiabatic lapse rate. Once it condenses and it moves upward, then we will say it is a moist adiabatic lapse rate. And environmental lapse rate is usually the lapse rate of the surroundings. Okay, this environmental lapse rate is driving the upward motion or downward motion. If it is having a temperature higher than our lapse rate, if the temperature is higher in the air parcel compared to the surroundings, it will be moving upward. So that energy will be there and it will be moving upward. So certain values are there. The moist adiabatic lapse rate I have given, I think it is nearly 6. 6 point something, and the adiabatic lapse rate is 9.8 degrees centigrade per kilometer.
Can I ask, what is opinion you people want to go in by 230 or that maybe better or? So because we are taking from Canada.
Sorry, I didn't check the time.
Yeah. 120. Okay, so please come by 230. Yeah. You want to summarize now?
Okay, like I have got only the basics. I think many of you have heard all the things before. Question. In a വേറൊരു
Yeah, you can. I think it's about scales of motion. Scales of motion. Scales of motion is there.
Okay, this is like I think we can finish now.
Yeah. Then we'll wait for some more time.
For 10 minutes.
The 230 we can definitely have one interaction session.
So, basic forces are there. You know, we said about gravity. Another force is pressure gradient force that also due to the change in pressure or the motion of the air mass will be determined due to the change in pressure that will be driving the movement of air mass. That is a change in the force generated by the change in pressure that drives the movement of air is called pressure gradient force. So a primary driver of air motion, and another thing is the Coriolis force. It's not a real force, it is an apparent force because the Earth is moving, like the frame of reference. When we consider if we consider the movement of Earth also, we feel like the parcel when a parcel moves from north, like in the northern hemisphere, if a parcel moves from south to north, we see an inclined path. If we visualize it from outside the frame of like it is in the earth, the parcel is in the earth, and the earth is the frame of reference. So due to the movement of this earth, that parcel will be moving, taking an inclined path. Okay, so that inclined path is towards the left or anti-cyclonic in the northern hemisphere and cyclonic in the southern hemisphere. That usually one if we we can demonstrate that if we rotate a table and we one table, if we are rotating it in the west to east direction and we are placing a marble in it and we are observing, we can clearly see when we move the marble like this, we'll be seeing the marble will be taking an inclined path. On textbook, actually that demonstration, that thing is there in that book, Wallace and House, Atmospheric Science and Introductory Survey, that experiment is given in detail. So due to the visualization or the change in the frame of reference, Earth itself is rotating. So if we are visualizing the movement of an air parcel from another place, then we see that the parcel is taking an inclined path. Okay, that inclined the force that is causing the inclined motion of the particle or the air parcel is called Coriolis force. And frictional drag also, we know all these are the four major forces that govern the atmosphere: gravitational force, the pressure gradient force, this apparent force, Coriolis force, and the frictional force. So that equation for friction is given here. It is the shear, simply the change in shear with height. That is the change in the resistance caused by the layers, different layers. That is called shear, the change in movement, because due to if it is nearby the layer, the friction will be more. That shear will be changing when it changes height. The change in shear is simply represented as the tau, d tau by dz there. So you know all this the things, troughs and ridges are there. So if we are having a low pressure system and it is simply a circular, it's a circular pattern of isobars, it is simply a low depression or deep depression like that. If we join all these pressure, we draw isobars. If you join all these low pressure area and it is representing an elongated system, you always seen in weather charts and weather reports, we see this trough is present there. It is actually an elongated system. Elongated, we join the isobars over a weather map and we are getting an elongated system. That is the pressure, it will be like having an elongated shape. It is called a trough, and ridge is another thing, that is an elongated area of high pressure, it is called ridge. And another concept is like air mass. You always say about air mass. That is a large body of air that is having the properties of the surface below. Okay, that is called an air mass. So we are having, if the monsoon time, will be having a certain, the air mass will be having a certain kind of properties, and it will be certain. The incoming monsoon current will be bringing more changes to the properties. Okay, so it will be having some maritime properties, the temperature characteristics of like that of from the ocean, it will be coming. So all these air masses, it will be remaining somewhere. It will be constantly not remaining. It will be moving, and it will be taking the properties from the surroundings as well as the properties of the surface. The heat radiated from the surface, all this, the pressure, all these things, it will be the radiations is there. So maritime or tropical air mass is there, continental polar air mass, that is polar present over the poles over the continents. So the frontal system is basically the boundary between two different air masses. That is, if two different air masses come together, there will be a strong change of properties between their boundaries. So that is called a front. So a frontal system is that, and that is a region of strong horizontal gradients of properties. That is temperature, pressure, humidity, and weight. This is basically the main scales of. We have seen this mesoscale forecast and all. It is how much it is like on a kilometers of. The forecast is given from a scale of kilometers to hundreds of kilometers. It is mesoscale. Below that is some turbulence. If this building, it is having some turbulence, it is generating some heat, it is having some turbulence, it is called we can say it is a micro scale one. And synoptic scale is like large cyclones, or we said about the troughs and ridges, that like in these maps and reports, all these troughs, and it is extended to a certain height, it is said like that, no? So all these are synoptic scale systems, and all the wind systems are Hadley cell, paracel, and polar cell. That global wind systems are there, no? It's rising from the equator, and ending at what is it? Subtropics, and it is again rising from there. So like that. So all these things are global planetary scale systems. So these are the different scales of atmospheric motion. Micro scale is there, mesoscale is there, synoptic scale, and global scale. So we define all the systems in this scale. And this you already know that sun earth geometry is there. The solar constant is the main solar flux, that is the energy received at the top of the atmosphere. And also another parameter is the Earth's angular velocity. It is the value is like 7.292 into 10 raised to that is about 10 raised to minus 5 radians per second. So actually all these we can elaborate if there are a lot of things are there. I think in the coming classes
we can have
solstices and equinoxes also. It's also important in the case of seasons. Thank you.
Okay, 2:30. Yeah. So tomorrow classes will be 11 o'clock. Okay. So I'll send a reminder. Okay. So tomorrow remote sensing basics will be covered. Two classes will be there. Afternoon will be also.
അല്ല എന്റെ കയ്യിൽ വെള്ളം
The room will assign you. That keep it there. This one also will take.